And here we go. Okay, so this was the assignment that was given to you last week. And of course, we are going to hopefully annotate this. Okay, so basically we had to design a single span floor joist and bearing length for the following conditions. So we had a joist spacing of 300 millimeters, and keep in mind, guys, I'll repeat it now so that the typical joist spacing for a floor is you start at 400, okay, and you try to design it for 400 spacing. And then if you run into a problem that there's too much of a load, then you can go and reduce it to 300, which will reduce the tributary width, and maybe that will work. And then ultimately, if that doesn't work, you might consider doubling up your joist. Anyways, all I'm saying is that start for a floor, don't go over 400, and stay between 300 and 400 for the spacing for floor joists. That's the most typical spacing we have for floor joists. Okay, so now the joist span is 4 meters, okay, which is a relatively good span for joists. And we had the specified dead load was 0.6 kPa and includes the weight of the joist. I just wanted to throw that in so people don't have to say, well, what about the weight of the joist? Now we have 2.4 kPa, so this could be a commercial, this can be a commercial floor. And we have a permanent load duration. So therefore, that's going to modify something in our calculations. And we have wet service conditions. Great. I thought I'd throw everything, and we might as well use treated wood. So now, and of course, fully laterally supported by the subfloor. So that means that your KL value is 1.0, and therefore, at least you won't have to worry about that factor when you want to go look at the values of the materials of the joist table. And of course, a case 2 system, that means you're going to have at least 3/8 of an inch or 9.5 millimeter plywood attached to the top of the joist, and it's going to be nailed according to what a case 2 system needs, and so on. So that's going to allow you to get a better value for the moment resistance and shears for the joist. And of course, I'm always going to ask you to use SPF number 1, number 2, sawed lumber, because that is the most common lumber you'll find in the lumber yards in Quebec. And that's it. So now, what we always do is we take our specified loads and we turn them into design loads. And by design loads, we mean what we'll factor them. And of course, case 1, okay. I'm doing this so that you remember that sometimes the dead load can be substantially high. If the dead load ever happens to be 10 times greater than your live load, believe it or not, your case 1 will govern your design. Case 2, of course, the dead load now goes from 1.4, the dead load factor, down to 1.25, and your live load factor is always 1.5. So this one is the one that governs. Now, what we do is we want to calculate what WF is, because we want to be able to analyze the joist. Therefore, we take the factor load multiplied by the tributary width. And of course, when you have members that are evenly spaced across your floor, the tributary width is equal to the joist spacing. Okay, so each joist will be able to carry the joist spacing, in other words. And in this case here, we have 4.35 times this joist spacing of 0.3, we end up with 1.31 kilonewton per meter. Now, here, there is nothing said about material susceptible to cracking, but this standard requires that the minimum, or I should say the maximum deflection that your member should have is L over 180, and therefore for L over 180, you have to take the total specified load and then multiplied by the tributary width. So in other words, here you don't see WD, you don't see WL, you don't see WS, it's W. In other words, the total specified load. It's not F because it's not factored. You always use specified loads. And we add them both up together, and therefore this is going to be the total load that you're going to put in your joist, and you're going to limit the deflection to L over 180. If I don't say it, that's the code. The very first class, when I talked about serviceability, I told you that the CSA 086 code requires for the total load a maximum deflection of L over 180. So now I calculate my MF, of course, simply supported, and therefore I have WFL squared over 8. And I get my moment, MF. And then after that, I have VF, WFL over 2. I get my VF value. And of course, I want to calculate the stiffness required for the joist, and therefore that's what I was telling you, L over 180 is the delta required for that, and therefore this becomes L cubed, and therefore this ends up getting to be 135 times 10 to the 9th Newton millimeter squared. So I'll leave it there so you guys can check your answers. If you didn't get exactly the same answer, I might have made a mistake, guys. I do make mistakes. If everybody else got the same answers, we're all on the same track.
I have
So
a quick question.
yes,
For your ESI, how do you know when you're going to use 180 or 160 or 360? Like which
if
formula? Because
okay,
I'm mixed up on that.
okay, okay. If your beam or if your joist, whatever is supporting a floor or a roof, whatever, okay? In other words, it can be your beam, it can be your joist. It doesn't matter what it is, as long as it's supporting a floor or a roof, okay? So
Okay.
for example, if that floor or that roof is not supporting anything that's susceptible to cracking, the most typical thing that we use in construction that is susceptible to cracking is gypsum board, okay?
Okay.
So if you know the architect is going to be installing gypsum board, even if it's a roof, and he's going to be installing gypsum board on the underside of your joist, okay?
Hmm.
Now, in order for you to avoid those things to crack, you should limit the deflection to L over 360. But in that case, you only take either your live load or your snow load. That's the only thing you take into consideration, okay? Now, if there is no material susceptible to cracking, this standard requires that a maximum deflection of delta is equal to L over 180. So you should check both and see which one governs.
Okay.
But in this case here, there was no material susceptible to crack, and therefore I don't have to check the L over 360. But
Okay. I
okay,
understand.
you understand?
Thank you.
Okay, so that's how when you, and then like I said, Adam, you got to keep in mind L over 360 is what the standard doesn't require it, but the National Building Code requires it. Okay,
Okay.
so that's a good thing. And if you want to always be safe, okay, if you like, I'm sure you should check both. And in most cases, unless your dead load exceeds your live load, okay, if your dead load doesn't exceed live load, I can tell you right now, L over 360 will always govern over L over 180.
Okay. So if it's susceptible to cracking or any materials we use, okay. All
Okay,
right.
so in other
Thank
words,
you.
if you're designing a floor for your parents' house and they know they're going to be putting some nice ceramics on the floor, okay,
Mm-hmm.
or they're going to be attaching gypsum underneath to finish the room below your floor, okay, then you should use minimum L over 360.
Okay.
Okay,
Thank you.
you're welcome. Okay, so now, of course, what's our design objective? Always to make sure that the MR value is greater than the MF value. And in this case, the MF value is 2.62. We have to make sure the VR value is greater than the VF value, okay? And of course, the stiffness provided should be greater than the stiffness required. So that's always our design objective. MR greater than MF, VR greater than VF, and ES provided greater than ES required. Now, we know that if we go to the joist checklist, okay, to verify that the tabulated resistance and ES values are appropriate for the structure being designed, the following questions should be asked, okay? So in other words, you're only allowed using the values in the tables if the load duration is standard. In other words, are you just applying a snow load or a live load? If the answer is no, then you have to modify the values in the table. And then the other one is the serving condition, in other words, what this is telling you is that is your KD value here for standard, is your KD value equal to 1.0? Yes or no? If it's no, then you cannot, you should not be using the values in the table, or you should be modifying the values in the table. Is the service condition dry? In other words, is your KS value equal to 1.0? If it's no, then you should not use the values in the table. You have to modify them. And then is the material free of incision or strength? And is the material treated? So, and then it says, are there any notches? So like I said, I don't waste my time with notches. The chances that you're going to be doing notches one day, if ever, like I said, send me an email. I will scan and I will copy the section with the notches. I'll be more than happy to send it to you. You understand? Does the construction provide lateral stability? This is a very important question. And of course, if you're building a floor and you're going to be putting sheeting on top of it, and you're going to be nailing the sheeting properly, and you're going to have a case two system developing from that whole construction assembly, and at the end, so the answer is yes. So this is a very important one to say yes to. And of course, is the construction provide lateral stability? In other words, here's my joist, here's my sheeting going across it. Because it's being nailed here, the joist will not be able to move out of place, and therefore the joist has this lateral stability, okay? That's what they're saying. It's similar to that LU that we did in steel, okay? And of course, okay? And then it says, if the answers to any of these questions is no, which is no, 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 yes, and yes, so any of them, okay? Okay, refer to the description of the modification factors below to make sure that the necessary adjustments to the table and DS values. Otherwise, if you say yes, 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 you can use the value in the table. So that's what I like about these checklists. They are very, very, aid memoir. They help you to remember that unless it's standard, unless it's dry, unless it's untreated, unless there's no notches, unless it's, laterally stable, don't use the values. You got to do something. So now so here we go. So that means that now, like I said, what they're saying is you've got to go you take the MR value in the table and you multiply by the modification factor, multiply by the modification factor, multiply by the modification factor. Now you can do that, but what I like to do is use my common sense, okay? I like to use my common sense and say, instead of worrying about taking the value, why don't I just take these values and bring them to this side? In other words, why don't I just find the MR value by taking my MF value and then dividing it by these factors? So I'll have to see what's the minimum value of MR has to be so that when I go to the table and I actually use it and stick it here, it will be bigger than this value. So this is common sense, okay? This is not even the handbook. This is me that came up with this common sense way of making sure that I can go and find the value of MR in the table right away, okay? And the same thing for VR. In other words, you take your VF value and you simply divide all the factors that will affect the VR value here and therefore will affect the VF value here. And the same thing you do with the ASI provided. So therefore, these are what you should be doing. So therefore, I will modify this so I can go straight to the table and find these values. And of course, what are these values? Well, make sure you make yourself a copy of this table because you're probably going to need it for the test, okay? So this is the KD value. So KD value is, okay, very simple. For standard, it's always 1. In other words, if it's a snow load, if it's a live load, and combined with this dead load, you use 1. If it's short term, as a matter of fact, it only helps you if it's short term. So that here, it doesn't hurt you. It helps you if you take advantage of it. And we will take advantage of this when we're going to be doing form work. And of course, this is where it hurts you. If you forget that you have a long-term load and your KD value dropped down to 0.65, well, this is going to hurt you because you're losing 35% of the strength because you're not taking into account the load duration, okay? So your KD value here is 0.65, okay? And therefore, and that's whether you're doing it for the shear or you're doing it for the moment. So it makes no difference. So that's something that you have to really consider in your design. And then after that, you have, of course, for serviceability, you got to be careful because there's one for bending, SB is for bending, in other words, moment, and one for SV for shear. And then there's one for stiffness. Now this is for notches. I'm not worried about notches. So therefore, here's the value for bending, here's the value for shear, and here's the value for the stiffness, okay? For strength. And then KT. So KT is, if it's dry, it's even more severe than when it's wet. So, and since here it's going to be wet, I'm going to be using the KT value of 0.85. And it even affects, the KT will even affect the stiffness, and therefore under wet, I'm going to have to modify the KT value by 0.95. So this is where I come in and get the different factors that will, influence the values in the table. Oh, sorry, let me just minimize that. So here I take my MR value, and we saw that the KD value of 0.65, the KSB value of 0.8, and excuse me, the KSB value, okay, and the KT value for bending, and therefore now this is what I had, and this is what I really need to find in the table a value that's going to be greater than that. And the same thing that goes for shear. So for shear, the KD stays the same, but the KSV changes, but the KT for shear stays the same. And now the shear went up. Of course, not that it went up. The values in the table would have to be diminished, and therefore I need to find a value in the table that's going to be greater than that. And the same thing happens for the stiffness. So for the stiffness, I have ES provided. Instead of having 135, the ES in the table has to have at least a value of 151. I hope that's clear to everybody. Is that okay? Can I go on?
Yeah.
Thank you. Okay, so there we go. And now that I've got my 3 new values, of course, I can go to the table, and which makes it very easy for me to go to the table, because now all I got to do is look for an MR value that's greater than the one I just calculated. So I start with the MR value here, which looks good. This looks good, and that looks good. So therefore, most likely, this will be my final choice, because I am in a case 2 system. In other words, I am allowed using the values here. So now, like I said, guys, this is the way I want to see you guys write the answer. You're going to write down the species, SPF, spruce pine fir, the grade, number 1, number 2. You're going to tell me what size of lumber you're using. So I know that you came here. And on top of that, you're going to tell me that, that the MR value is 5.72, whatever you took out from the, and of course, you give me no units, I give you 0, okay? And the MF value is greater than the MF value here. Well, this is not really the MF value, but I know that the MF value here, okay, when I take this value here and I multiply by all those factors, it will still be greater than that MF value that I originally did. And the same thing with the VR value. And then, of course, the ESI provided, so 390. So that means I've got my strength, I've got my serviceability, I've got the good member. Now, once I've chose my member, I have to go and decide how much of a bearing length minimum I need for this joist to sit on its support or its reaction area on the support. And therefore, I got to go calculate the bearing length. And of course, QR should be greater than or equal to QF. Now, what is QF? QF is a force that is perpendicular through the grain of the wood. So in other words, if you look, here's my joist like this, okay? And it's going to be sitting here somewhere, okay? And QF is a force that is perpendicular to the grain of the wood, okay? So what force right now do we have that's perpendicular to the wood that's going into the reaction area?
VF.
Well, do you agree? Or do you doubt yourself?
I agree.
Okay, so that's why. So I want you to understand that. In other words, so that's why we say in this case here, the QF is equal to the VF, right? Now, what happens, just for example, what happens if I would have a wall here, okay? If I would have a wall here and I'd have a load coming down, this would be a bearing wall, and I have a PF here, right? And I also would have my joist and a VF here. What would be the QF value then?
Would it be the PF plus the VF?
Exactly. In other words, you sum up all the forces that are going to be going again across the perpendicular to the grain of the wood, and therefore, in that case here, your QF would be equal to your PF plus your VF. And that's why you have to be careful when you have your joist sitting underneath a bearing wall, that you remember when you're looking at the bearing here, that you have to worry about the PF coming down from the bearing wall as well as the VF coming from your joist, okay? So that's good. Okay, so that's why in this case here, we go on. we have QF is equal to VF because we only have one vertical force perpendicular to the grain, which is our shear force. And therefore, we know that the big QR is equal to the small QR times the bearing length, and that should be equal to greater than or equal to the QF. Now here, we're using SPF. Now you'll note that QR does not, okay, the QR does not vary with grade. In other words, whether I'm using select structural, or I'm using number 1, number 2, or I'm using number 3 utility grade or stud grade, QR stays all the same. What is the width of my member? 38, and therefore my small QR value, and these are the units, kilonewtons per millimeter, is 0.161. So for every millimeter that this joist is going to be sitting on its support, it's going to be able to develop a resistance of 0.161 kilonewtons for every millimeter. So here I go. Now, guys, do not take the VF value that you modified for the joist and use that as your QF value and then go calculate QR. That is wrong because the modification factors here are not the same. Not all of them are the same like the ones for the beam. Okay, so that's why you shouldn't do that. In other words, you should take the VF value that you calculated when you did your analysis, okay, which is this value here, and then you modify your QR value according to the modification values for the force that is being applied perpendicular to the grain, okay? Now, so therefore, what I do is simply take the values in the table and multiply it by the factors that will affect the QR value, okay? Which is the simplest thing to do. And of course, okay, so here you go. So, you know, for the KD value is exactly the same. So that doesn't change. So here we have no problems. In other words, for this is KD. So the KD value, whether it's for bearing or if it's for the, you know, for the joist itself, but the KSP value changes. Okay, so the KSP value now goes down to 0.67 as opposed to the values that you saw in the table. Okay, so like for service, for bending, it was 0.84, for shear it was 0.96. So that's why you cannot use that value there. You have to come and find the KSCP. In other words, the service, compression, perpendicular, that's what this means. Service, compression, perpendicular to the grain. That's why they put this subscript here. And the KT value, they could be the same or they can be different. So the KT value here for wet is 0.85. It happens to be the same. The KD value is the same as we used before, but the KSCP value is totally different. So that's why you cannot use that value that you modified for your joist and then calculate your bearing. I see that classic mistake every year and I penalize the guys severely for it. So keep that in mind because you are making a mistake. So here we go. So now all I got to do is take this value here, this resistance here, and multiply by those factors. And then of course I will end up getting, so this means that the minimum bearing length that this member should be sitting on its support is 0.4 kilonewtons. So that means that, okay, so if I go to a job site and this is, for example, whatever the support is, this could be a beam or a wall, and I see the carpenter is putting the joist right here like this for some reason, and he's giving me something less than 44 millimeters, I'm gonna say, no good, okay? So and then if I go to the job site and I see that this is a 2x4 wall, and I know that this is 89 millimeters, and I know that there's a header joist here that's going to take away 38 millimeters, and therefore, the joist sits here, and it's going to be more than 44 millimeters. I'm going to say perfect. That's exactly what I need. I need at least 44 millimeters. So as long as what they're providing for me at the job site exceeds what's required, I'm okay. But as soon as I see something that is less than what's required, I put up a stink, okay? And that's it. Any questions?
Yes, sir. Just one question. Can you go back to when you calculated ESI? Because I'm getting a different value, and I don't know why. I've been trying to figure out.
Okay, let me hear.
You go 151 times 10 to the power 9.
150. Yeah, that's what you get.
Sir, because we use the same KT. We used the 0.85 instead of using 0.94. Right? So I did the same mistake.
Oh, okay.
Yeah, because there's a different for ESI. There's a different KT we have to use.
So in other words, what you're saying is that here you didn't use 0.94 and 0.95.
I used 0.94 and my mistake is the 0.85. Okay.
Okay, so be careful. Like the modification factors, they're there on the sheet. It's clear. So that's your little mistake right there, Adam. Okay.
Okay.
Fair enough. Look, like I said, if this is the mistake you make, it's, for me, that's minor. You understand? As a matter of fact, it has no consequences because that means that you used something here that was smaller. You ended up with something even higher here.
Yeah, I got 169.
So that means that you did not really penalize yourself in the wrong way. You penalize yourself in the right way. You're asking it to be even stronger than what you actually need. So, you know, I will still penalize you because it's incorrect, but it doesn't penalize you in real life. It wouldn't penalize you. You understand?
Okay.
And then on top of that, Adam, just to make sure that we understand each other, look, even if you have made a mistake of 200 here, and look what you actually have.
Yeah, 390.
See, so you know you've got a good margin before like this thing can ever have any consequences on you. Okay.
Okay.
But not academically, because even in real life, even though this thing has no bearing, and somebody would ask you for your calculations, and this would be like become a problem because there's a mistake somewhere, they would make a lot of smoke with this mistake. Oh, look, the guy can't calculate properly. He made a small, and judges don't understand the difference. You understand? And that's why I want everything to be perfect. So this way, you know, like that's why I'm being a stick in the mud. You understand? Because I know how much smoke people make when it's not really necessary. Okay. Okay, so that was it for the assignment. For those of you that didn't even bother downloading the assignment, trust me, I know who you are. That's one thing I like about Leah. Okay, so it would be nice that at least you download it. I'm not saying that you have to try it, but you know, there was 4 people that didn't even bother trying to download the assignment. So I know next time you probably download and won't even try it, but you know, like I said. Now, what we'll do is, of course, we'll move on to the okay, hold on a second. Assignment number 1, I want to close that. Looking for the wood lecture. Okay, so today we're going to move on and we'll learn, like now that we know how to design joists, right? The next thing that we're going to learn how to do is we're going to learn how to, excuse me, we're going to learn how to design built-up beams, okay? And, we'll, you know, so let me get to, let me dock this at the bottom. I like it better at the bottom. Sorry, guys. Okay, and let me dock this, oops, let me dock this at the bottom. Okay, now, before we get into built-up beams, somebody asked me last week about engineering joists. I forgot, who asked me, somebody had a question about engineering joists last week.
Yeah, I asked it.
Okay, so Alex, is there something in particular you want to know about engineering joists, or you just were asking me in general what they are?
Well, I was just wondering if it was like the same way to choose the joist, if it was like the same to choose like a 2x4 or a 2x6.
No. First of all, engineering joists, they look like this, okay? That's what they look like. You understand? In other words, the top and bottom chord is made with a piece of lumber, okay? Like here, this is made with, you see this one's made with a 2x2, this one's made with a 2x3, this one's made with a, you understand? So these are pieces of lumber, okay? It could be a 2x4, it can be a 2x3, and then of course the web members are made with these OSB boards. Okay, so those are engineering joists. If you want, I can give you manufacturers and you can go to their website and you can look at their catalogs. As a matter of fact, I can send, you know, but so, and the thing about engineering joists is that you'll have span tables in engineering joists. And basically what they'll tell you is that this joist for this span can carry this load or can so many pounds per square foot or so many, you understand? So that's already worked out for you. So all you really have to do is know your loads, just like we did, for example, when you went to the open wave steel joists the manufacturers. As long as we knew what our loads were, we were able to pick right away from the catalog what we needed in terms of a depth. You understand? So that's all it is. Like, and you know, if I think about it, next week during one of the lab, I'll probably find I'll get a manufacturer's catalog and I'll show it on I'll show it during the lab, and this you guys can get an idea of what we mean by span tables. You know, like for me, it's, you know, span tables. Like I figure that I think you guys will be smart enough to realize what you need to do with it. So, but if you don't, I'll be more than happy to find one. I'll find you a manufacturer that here in Quebec. Okay, I know a couple of them. It's just that I haven't been practicing for such a long time, so I'm really out of touch with the industry. Jaeger used to be a big manufacturer. I don't know if they're still around. So I'll look around and I'll try to find one. And if I can find one, I'll be more than happy to show you how easy it is to. I love these manufacturers because what they do sometimes, they even give you like the software. So you just give them your geometry, you give them your loads, and the software will actually calculate for you what you need, you understand? And they'll even calculate the bearing. Really nice, okay? So, okay, now what's important here, what I like to stress about these things, okay? What's important here is that sometimes, okay, sometimes, many times, does everybody know that you guys learned in construction 1 or construction 2, you learned platform construction versus balloon framing construction?
Yeah,
yes,
we did.
Yes, we did.
Yeah, we learned it.
Yes, sir.
We did.
Okay, now like today, I don't know if they told you this in the construction 1 class, but 99% of wood framing is done with platform construction. Everybody knows that?
Yeah.
Balloon framing is used very little.
Well, sir, just to refresh my memory, isn't balloon framing like an older method that used to be used a lot and then kind of got replaced by platform?
No, balloon means that the vertical members that hold that will support the floor will go through the floor. That's all it means. Okay, so you can still use balloon method today. It's just that it's the older way of doing it, and especially when you'd have, like they call in French, le quart plein. You understand? In other words, you would be making it with solid timber because there was no insulation. They would make sure that the solid timber members would go right through, and then the floor would hang on to these walls. You understand? So you're right. You understand? That's how, and that's what balloon framing was. But you can still do balloon framing today if you want. You understand? But so what that means is that, okay, so what that means is balloon framing means, I mean, platform framing means that, oh, sorry, why did I pick such a heavy, okay, sorry. Okay, so that means that here's my floor, okay? So when you're making a platform, here's my floor. And then you can have a wall here, like this, let's say your foundation wall, okay? So these are the engineering joists that you have, okay? So and then after that, so they're supported on the foundation wall, whatever. And then after that, they got a bearing wall that comes down like this, okay? And it's sitting on top of the joist instead of the joist sitting, okay? And then you have another floor here, and you have another bearing wall. So you can see what's happening. And then I've seen this 3-story buildings, okay? This is how they were built, okay? They were built platform construction, 1 floor, 2 floors, 3 floors. And then on top of that, you even had the roof sitting on the exterior wall, and all the loads were coming down, okay? And going through all this little, without anything here to transfer all this load, and it was completely relying on this to transfer all that load down to the foundation. These things buckled. They had to evacuate the building, okay? They had to evacuate the building in the middle of the night, and I'm telling you, just because the idiots didn't realize that all they had to do was, okay, they had to just have some kind of blocking here so that instead of the load going right through this little web, it would get transferred either through a rim joist, either through blocking, or you can put things perpendicular. So guys, if ever you go on a job site and you see that there's platform construction, okay, the platform construction, and it's going to be 2 to 3 stories, even if it's just 1 story, okay, and if you see where the bearing walls are sitting on top of the floor, and if you don't see any rim joists here or squash blocks here or something that's running parallel to that wall to help transfer that load, raise hell, because it's going to become problematic. And if ever you buy this building, by the time you buy the building, everything is finished off, the ceilings are finished off, you don't see nothing anymore. And it's only like all of a sudden when the place gets occupied and it starts snowing and it's in the middle of the night and all of a sudden, bang, it starts to collapse. And then when that happens, the fire department comes in, sees what the problem is, tells everybody in the middle of the night, get out, you can't stay in your building anymore, and you got to abandon your building. Okay, why? Because they forgot to put one of these little pieces of wood to help transfer the load that comes from all the way from the roof down into the foundation wall. And that's very, very important. Okay.
So sir, the rim joist is gonna run along the whole span.
The whole length, and therefore all the wall is gonna, most of the wall is gonna get transferred. In other words, exactly, this rim joist goes all along the wall. You understand? These squash boxes are placed at every joist. You understand? And this here, like if you want to use it, this is the I joist. This is also running all along the wall. You understand?
Yeah.
My preference is this. Squash blocks, okay? And look what they say. Squash blocks on outside of joist, put one on each side, okay? Cut to a length of 2 millimeters shorter than the joist depth. Isn't that nice? They even want you to make it just a little bit smaller. 2 millimeters is peanuts, but you understand? So this here, for example, okay, and I'm telling you guys, it's really sad. And I mean, and guys, when this happens, you're looking at mega bucks to fix, because now the floors are all down, all kinds of damage that have been caused to the finishes and the floors and all that, all because some idiot forgot to add a piece of wood that would probably cost peanuts to do. You understand? So this is one thing I want you guys to keep in mind. If ever you're buying a condo is 3 stories high, and all of a sudden you ask the guy to give you the shop drawings, and if on the shop drawings of the flooring you don't see these squash blocks been placed, okay, don't buy the building. You understand? Stay away from it. That's all I can tell you. So that's what I really wanted to stress, that because I've been involved in a file that had this problem, and trust me, to correct it it's doable but very expensive. Okay, so I was involved. And then on top of that, there's one of your predecessors that graduated from the program. I think she graduated back in 2004. She moved up to somewhere in Alberta. I think she was in Grand Prairie or something, not Grand Prairie. She was in her building had this problem. And she sent me an email saying, sir, stress to your students about the importance of putting these things in a wood frame construction. She had to evacuate from her building in the middle of the night by the fire department. Okay. So this is like, it's happening not only here in Montreal. I hope the manufacturers or the suppliers, the fabricators of these joists, okay, have the detailer smart enough to realize that as soon as the load is going through the joist, to provide some kind of load transfer mechanism, either a rim joist, squash blocks, or at least another I joist to help transfer that load, instead of just relying on this little piece of wood here to transfer that load. Okay. Really sad. So, and that's something that you should always keep in mind. Hold on a second. So that's what I want to say about engineering joists. Okay. So, and very, very important. Okay. So like I said, guys, I like to stress on things where I know that are problematic, instead of giving you a lot of stuff that might not have any, you might not even come across in your career. So. Okay, so now built-up beams. What's a built-up beam? Well, here's a description, okay? A built-up beam are composed of 2 or more lumber members. In other words, everybody know what I mean by lumber. Plies fastened together side by side with bolts or nails. So in other words, you can nail them together, you can bolt them together, and we'll see when you should bolt them and when you can just nail them, okay? So what this means is, the plies should be continuous between the points of support. However, Part 9 of the National Building Code permits the built-up beam to have butt joints at either 150 millimeters at the end quarters of the quarter spans and the built-up beam. Now, so that you guys can appreciate, okay, so that we're gonna look at the thing. Okay, might as well, I'll show it to you here, okay? So here. So this is a built-up beam. In other words, this is a joist. this could be a 2x4, a 2x6, a 2x8, a 2x10, or a 2x12. In other words, 38 by 184, 38 by 235, 38 by 286. Okay, it doesn't matter what it is. Okay, so these are what we call plies. In other words, if I have 3 2x12s, it becomes a 3-ply. If I have 4, it becomes a 4-ply, and so on and so on. So that's what they mean by a built-up beam. Now, what they're talking about is that this is a butt joint. In other words, where one member, okay, butts up against another member, okay, to make the beam. So in other words, here, this member butts up to that member. They're saying that where it's L, in other words, at 1/4 of the span, plus or minus 150, okay, this is the only place you're allowed to have those butt joints. Otherwise, okay, the only place that you should really be putting your butt joints would be right over your reaction area here, okay? So, so this is what they're saying, that if you want, you can have butt joints, but they're only allowed in this location and in this location. So this is where you're allowed to have butt joints. Although if you should not have a butt joint there, because that's where the bending is the highest, and therefore all the fibers have to work together. So it's as if like I'm trying to get this beam to bend, and then all of a sudden I only have 2 plies that are working in bending. So this is never have any joints where the moment is the highest. Okay, fair enough. And therefore the only place you're allowed to have your butt joints is here, in these areas here. In other words, where the shear is what's going to basically be high in this area, but we know that the shear force of the lumber can probably resist it. So, okay. So that's what you're allowed to, okay. So now, so does everybody understand? So is there any questions regarding this diagram?
How do they put the beams together? I'm guessing they compress them and they like nail it in together, or do they just use adhesive?
Okay, you want to know how the carpenters really do this?
Yeah.
Okay, I'll tell you. Okay, that to show you, this is the smart carpenters, not the dumb ones, Gordon. Okay. Okay, in plan view, this is my plan view. Okay. Now, normally you don't start framing anything until your foundation walls have been poured. Fair enough?
Yeah.
Okay. And let's say, I don't care in which direction. Let's say your beam is running in this direction here, or this direction. I really don't care. Okay. Doesn't matter which direction. So let's say this is your beam right here, your built-up beam, and of course there are going to be columns here eventually, right? So what the carpenter does, in other words, if this happens to be made with, what do you want to make them with? 2x10s, 2x12s? Is that what you want to make them with? Huh?
Yeah, sure. 2x10s work.
Whatever. Okay. So what the carpenter does is he takes this 2x10 16-footer. Okay. He puts it on top of the wall here. He takes the other one next to it, and he puts the other one next to it. Then he takes the next one and he makes sure that the joint falls here. And then he puts the one on top, you know what I mean? Like he staggers the joints so that they don't fall, they fall according to this. And then he just nails that ply to that ply. And then he puts his 3rd layer and he nails. And then he puts his 4th layer and he nails. Then once he's built up his beam, what they do is they just rotate the beam, boom, 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 on this foundation wall, and they drop it into place. So they don't even have to lift it. Isn't that smart?
Yeah, thank you.
Okay. So that's how, that's if you're asking me how would I build up the beam at my place, if I was doing a country place, I would build it on the wall here, you know, 1 ply and have it all nailed together and everything. And then I would twist it, you understand, tip it and make it fall here, make it fall there until where I need to place it. And then I would finally put it in this position, and then I would go and put the columns underneath to support it properly. Okay. That's how the smart carpenters do it. I don't know how the other guys do it. So. Okay, so now more details about built-up beams that you guys should keep in mind. Okay, where possible, built-up beams should be top-loaded. Okay, now what that means is okay, so here is my beam in cross section. I'm looking at a beam, so I have like 1, 2, it doesn't matter how many plies. Okay, there's my beam. Of course, it's going to have some kind of support underneath it. Okay. Now, what they're saying is that if the floor joists are going to be resting on top of it like this to be supported, then this is top loaded. If I'm going to have joist hangers here, like I can have joist hangers here, and if the joists are being supported on the side, and of course that's side loaded. And then of course, this one, you have to be a little bit careful on how many plies, anyways, you'll see, okay? So if you can, you should top load, but since some people would like to have that headroom and they want to put that beam as high into the floor as possible, therefore the beam becomes side loaded. That's why, you know, but you know, if there's no concern about trying to have some headroom, in other words, having that extra, losing that extra, whatever it is, 10 inches of clearance in your room, because nobody's going to go down there, then I do recommend that you top load your beam, okay? Now, so that's top loaded, and that's okay. So when side loaded, fasten between plies is critical, okay? Bolts, nails, or screws may be used for the, and follow design procedures recommended, okay? So now, determine the loading that must be transferred from the outer ply to the inner ply. So when you're side loading, you're gonna have to, you know, do a little bit more than if it's top loaded. If it's top loaded, you just nail it, you don't care, okay? But when it's side loaded, well, this is what you need to do. For instance, for a 3-ply beam loaded on one side, 2/3 of the load must be transferred from the outer ply to the 2 adjacent plies. So you have to make sure that you're, like, if in other words, here's here, okay? Here's 1 ply, here's 2 plies, here's 3 plies, and even if I have a 4-ply or a 5-ply, it can go up to 5 plies, okay? So what they're saying here, okay, is that if I'm gonna be side loading here, like this, and this is my joist sitting here, I gotta make sure that the fastener I put here that will go into here will transfer 2/3 of the load as it's transferred from the outer ply. So in other words, 2/3 of this load has to make sure it gets to these 2 plies. And that's, you're gonna, and when we get into fasteners, I'll show you, if and when I'll show you how to do that, okay? That's gonna be towards the end of the semester, okay? Calculate the lateral resistance of the, calculate the lateral resistance of the fasteners to be used, okay? So in other words, you have to calculate this. Determine the spacing of the fastener required by dividing the load, okay, step 1 and to step 2, okay? So if you're gonna side load, you better make sure that, okay, that these fasteners can actually transfer that load into the inner ply. In other words, what they don't want you to do is all of a sudden, this is what they don't want you to do. You have to make sure that, here, I'm gonna put 1 little nail here, okay, like that. And then when it's side loaded, this ply decides to open up like this, and the whole thing starts to fall. So you want to make sure that the whole beam works together to carry that load, okay? So and that's where, when I side load something, okay, I will actually bolt right across to make sure everything's working together. So just to, you know, I won't rely on nails anymore. I will actually bolt the thing together, and I will determine how far the bolting has to be, and so on and so on, okay? Or if I don't want to bolt, I will use lag screws, and I will make sure that the lag screw goes in far enough that everything gets, so it's either bolted, lag screw, but I will not rely on nails when it comes to side loaded beams. And the other good thing that you can do, okay, is that if ever you have a built up beam, one of the things that you can, okay, or you should specify, is that they put an adhesive in between each ply before they put the fastener. So this way each ply can actually glue together, and therefore that can even further increase, you know, and minimize the chance that this thing will ever slip. Like the last built up beam that I built was a couple of years ago. I went to the store, I bought some PL glue, you know, like PL is the brand name that you can find that it's in a wooden adhesive. Put it in between the plies, and then when we screwed the thing together, the glue oozed out. So I knew that it was all glued there properly, and therefore I knew between the screws and the glue, I had no problems, even though it was side loaded. Understand? So that's another thing that you should keep in mind. You might want to even specify an adhesive in between each ply. So, Okay, so be careful when you're side loading the beam. If it's top loaded, like they said, when it's top loaded, for top loaded beams, very simple. The individual plies should be fastened together. The fastened spacing should be no greater than 4 times the beam depth. So in other words, what this guy says, if you have a beam depth of 8 inches, don't put your nails further than 30 inches apart, which nobody does. Everybody puts them at about 12 to 16 inches apart. So that's how simple it is. So top loaded, just nail it. Don't worry about it because the load is going to be applied to the top. There's no problem that this thing can open up on you. But if it's side loaded, keep in mind that it can become critical, okay? So nails are not recommended for side loaded beams with more than 4 plies. Further, 4 and 5 ply beams are recommended only when the loads are applied on both sides. That's something else, okay? Now, so for example, if I have a built-up beam here like this, okay, if I have a built-up beam here, and if I don't have the floor being supported on both sides of the beam here, this way, they do not recommend that you side load the beams if you're just going to have the beam on one side like this and the floor joists are just on one side. So this is not recommended, okay? If you're going to have that, make sure it's top loaded. That's what they're saying. You can still have a built-up beam just for one side, but make sure it's top loaded. Because what's going to happen is that this beam can start twisting on you, okay? And then you can have another problem if it's not really well stabilized. So that's what they're trying to caution you here. Any questions here? So guys, this is something you should, if ever you decide to side load something, come back and read these notes very carefully, okay? And make sure you follow these instructions to the T, okay? So now, as far as, now, because we are using, okay, joists to make a built-up beam, in other words, we're going to be using 2x4s, 2x6s, 2x8s, 2x10s, 2x12. The same checklist for joists applies to built-up beams. I mean, we're using exactly the same members, and the only difference is that we're putting more of them together, closely together, and they're going to give us a better resistance. So therefore, the joist checklist is the one that applies to built-up beams, okay? So just like we did for joists, if the load duration is standard, KD is equal to 1. If the service condition is standard, KS is equal to 1. If it's untreated wood, KT is equal to 1. If there's no notches, KN is equal to 1. Okay, does the construction provide lateral stability for the joists? Okay, and of course the answer is 1 here. Okay, yes, because we're talking about the beam. Then we can use the values that we see in the built-up beam table because they are based on the fact that KD is 1, KS is 1, KT is 1, KN is 1, and of course everything's laterally stable, everything's stable. So this is here. Okay, now I hope, I don't know, this seems to be a little blurry to me. Is it my eyes? Anyways, I gave you, I sent with the class, I sent you another copy, another PDF, so you don't have to worry about this. So this is the built-up beam section. Like I said, you can only come to this table if and when you said yes, 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 yes to the joist tables. If you didn't, then you have to make modifications here like we did for the joists. Fair enough? And it's the same modification that applies here as what we did for the joist. Now, so here is, okay. So basically, very similar to the joist tables, very similar. In other words, they start off with the species, okay? Douglas fir, larch, okay? Hemlock and fir. And of course, SPF, spruce pine fir, and then there's northern. Now, we will never use this, so don't even bother with this part of the table. This is select structural. The chances you're going to find select structural at the lumber yard are almost, okay? And therefore, we will never use this. Now, the way it's broken down is that, are you going to be using 2 plies? Are you going to be using 3 plies? Are you going to be using 4 plies? Or are you going to be using 5 plies? Well, not are you going to be using, depending on the MR value that you need, depending on the VR value that you need, depending on the ESI value that you required, you're going to come to the table here, because this is what we're going to be using right here. Okay, so you're going to come to the table, you're going to look for an MR value greater than your MF value, you're going to look for your VR value greater than your VF value, you're going to look for an ES value greater than the ES required. And then once you find a table, you will go up and you will look at how many plies you have. You look at what member size gives you that resistance, and on top of that, you go look at how many plies. So that's what you do. So therefore, just like we did for a joist table, we'll go look for MR, go look for VR, go look for ESI required, provided versus ESI required. And once we find that met all of those three design criterias for strength and serviceability, then we know what size of member is going to give us that. And on top of that, we'll know how many plies are required in order to get that resistance. Now, there's something I want you to notice here, guys, okay? You'll notice that, not that I recommend you doing this, okay? But I just want you to be, okay? I want you to notice something. The table is good for a 2-ply. The table is good for a 3-ply. The table is good for a 4-ply. The table is good for a 5-ply. Is the table good for a 6-ply?
Yes.
Okay,
No.
and how would you get the values of the 6-ply?
1 second, let me figure out.
He will interpolate.
Sorry?
He will interpolate.
Yeah, you can interpolate. In other words, this is for 4-ply, this is for, like if you notice the difference between a 3-ply and a 4-ply, a 4-ply and a 5-ply, it's exactly the same difference. So each ply adds exactly the same amount of resistance. And therefore, if you want to go to a 6-ply, take the difference between here and here and add it to this, and that's going to give you the resistance for a 6-ply. Try it, you'll see. Like in other words, the difference between 24.2 and 18.2 is how much? 6.66, right? And the difference between 24.2 and 30.3 is 6.1. So therefore, if I had to go for a 4-ply, the MR value would be 36.3. You understand? So if you ever want to get up to a 6-ply for whatever reason, okay, you can still use this table to give you an idea what you would get in terms of a 6-ply. I'm just because the bending moment, because of the resistance, okay, because all these values are based on the B value here, okay, B, okay. So in other words, 1-ply, 2-ply, in other words, another B, another B. In other words, because everything is based only on one variable, and of course, as these they increase, then by adding another ply, all the values are linear. There's nothing squared, there's nothing quadratic, there's nothing cubic. So everything you can just extrapolate linearly if ever you want to get to a 6-ply. Okay. I don't bother with the 6-ply because sometimes that can be very heavy for the carpenters to actually move around. But if ever you don't have a choice, you want to use a built-up beam, and you can't put more columns in, and you're stuck with that span, and you're stuck with that lumber and whatever, well, that's a good way for you to get the values here. Okay, I just want to let you know. So clear all drawing. Not that I ever did it. I don't bother. I stay within this limit here. Okay, and therefore like I said, I don't want the beam to be too heavy. A 6-ply, depending on the length and all that. So I like to stay within this, but if you want to, you can, there's no problem. Okay, so does anybody have any questions with this table? I think it's still straightforward. Like I said, here's the grade, here are the species, here's the one that we're going to be using, okay? And it's very similar, okay? And here's the size of the lumber, okay? So in other words, you have a 2x6, a 2x8, 2x10, and a 2x12, okay? So that's the ones that, okay, it doesn't even start with a 2x4, it starts with a 2x6, and it works its way up. And of course, we're going to do an example, and we're going to, of course, apply this table to find the solution to our problem. So is everybody good with this? Or does anybody have any questions? Does anybody have any questions, or may I go on?
No. You can go on.
Okay.
Okay.
Hey, we're doing okay. Time-wise, we're doing good. Okay. So here we go. We're going to design a built-up beam and the bearing length, of course. We design a built-up beam and the bearing length supporting joists spanning 3 meters on one side and 3.6 meters on one side and 4.4 meters on the other side. So what this means is very simple, okay? And of course, what is it? Oh, oops, sorry. So, when you see this, for me, what I see what flashes through my mind, of course, I mean, it's because there's a big void up there, but what flashes through my mind is that here's a beam, okay? Okay, the span is 3.6 meters. That means it's sitting somewhere here and here. So that's my span. Okay. And then I have joists here that are sitting like this. And they're sitting somewhere else here. It can be on a wall here. And I have joists here that are sitting on a wall here. I should have drawn the joist a little bit smaller, but okay. And all of a sudden, the span of this joist here, we said was 3.6 meters. Oh, this is just, I don't have the span yet. Okay, so this is 3.6 meters, and this is 4.4 meters. Okay, sorry, I missed, okay. The span of the beam is 3.6 meters. Oh yeah, okay, so that's why I said 3.6. So that means that this span here is 3.6 meters, okay? So what's gonna happen if I do a cross section here, I should draw this, okay? So if I draw a cross section here, what I have here is I have a beam and the joists are sitting right on, like this is top loaded, okay? And of course it's supported there and it's supported there. Okay, and that's what you know, and therefore that's my geometry. And now the load duration is standard. So therefore KD is equal to 1. Dry service condition, because it's going to be built inside of a house, and because I'm building inside a house. So in other words, every residential house, you're going to have standard load condition, KD is equal to 1, KS is equal to 1, KT is equal to 1, because you're not going to use treated wood inside your house. So therefore you can go straight to the table because everything is 111. And therefore fully laterally supported by a full joist, that's important. In other words, make sure your beam is going to be, you know, attached, or the joists are going to be fastened or nailed to the beam somehow, so that the beam has the lateral support provided by the joist, you know. And that means your KL is going to be equal to 1. Now, the beam is supporting finishes susceptible to cracking. Now, I say finishes, like I said, it can be drywall, it can be ceramics, it can be whatever you want, okay? So beam supporting finishes susceptible to cracking, that tells me right away that I should limit the deflection of the beam, and even the joist, for that fact, to L over 360, okay? Now, what I do is just like I do for, this is very, very similar to the joist. The only difference is that the tributary width is going to be slightly different. So for load combination 1, I get 1.4 times D. So I get 1.125 kPa. And for case number 2, I end up getting 1.25 and 1.5 L. And of course, the higher of the two is the one that governs. So therefore, this becomes my design load right here, 4.64. Now, what I need to do is, of course, take this pressure. In other words, I shouldn't have erased it, but I should take this pressure and turn it into a uniformly distributed load, so I can know what's the load that's being carried by the beam. And of course, the WF, which is a uniformly distributed load, is the factor load times my tributary width. And guys, like, do this. This is the best way to minimize mistakes, okay? I suggest you do this, okay? And I do this constantly, even to this day, okay? What I do for the tributary width, I take half the sum of the joist spans on each side. So I add the two spans together, and then I divide by 2. So this way I won't make a mistake. I know that I have 3.6 on one side, I have 4.4 on the other side. So I take 3.6 plus 4.4, add them together, and then I divide by 2. And that gives me my tributary width. That is one of the ways that you can minimize making a mistake. So my tributary width, everybody can appreciate what I'm saying. Instead of saying, well, what's half of 3.6, 1.8? What's half of 4.4, 2.2? What's 1.8 plus 2.2? Well, just add the two spans together and then divide by 2. And that's going to give you a tributary width. And guys, like I said, this is only for your structure that all the members are simply supported, okay? Keep that in mind, okay? Because the real tributary width, if you want the definition of real tributary width, is from point of 0 shear to point of 0 shear, okay? Okay? And of course, that's the real tributary width. And when things are all simply supported, where is the point of 0 shear? At the center where the moment is maximum, and that's where we take half and half. So this only applies for simply supported members, okay? So now, WF, of course, 4.6 was my factor load multiplied by my tributary width. I end up with 18.4 kilonewtons per meter. Okay, of course, my loads are going to be a little bit higher than what we normally see on the joist because, of course, the tributary width is much bigger. Now, here, I'm always going to calculate the L over 180 because that's required by the standard. So I'm going to take my total load multiplied by my tributary width. That's for L over 180. And because I have susceptible, okay, so that's going to be W. And because I have finishes susceptible to cracking, well, in that case, I only take my live load. In other words, anything, I only take the live load and multiply that. I take WL and multiply by my tributary width. So this is for my stiffness, and of course, this here is for my strength. So now, what's MF? I mean, very simple. WFL squared over 8 because the beam is simply supported. And of course, here's my span, okay? And that's my WF, and therefore I end up with 29.8 kilonewton meter. That's my MF value. My VF value is WL over 2, 18.2 times that. And of course, now, this is for the total load. I take a deflection of L over 180. And then for the live load, I take a deflection of L over 360, okay? And of course, I can tell you right now that this is the one that's going to govern because the dead load does not exceed the live load. But I'd rather you guys do both so you can get into the habit of, And of course, so here the ESI required is 180 times 5 times WL to the third, and then the ESI required is 360. Of course, this L cancels that and brings that L to the third. And now I calculate them and I look at the two, and of course the higher one is the one that governs, and therefore this becomes the ESI required. 2,100 times 10 to the 9 Newton millimeter squared. Well, I've got everything now. I've got what I need for strength. I got what I need for serviceability. So I can go, and since I answered KD is 1, KS is 1, KT is 1, KL is 1, everything is 1. Yes, I can go straight to the built-up beam table. And of course, here, what I did, I extrapolated that one section that applies to us. And I usually like to start with, okay, I like to start with, so for example, can I get away with a 4-ply? No, because there's nothing here that's going to give me 29. I have no choice but to go with a 5-ply. Because sometimes you might be able to have either a 5-ply or a 4-ply. It happens, and it's up to you to choose which one you want. They're both correct as far as design goes. And I'll tell you which one I would use, okay? So in this case here, I would try a 5-ply. I have an MR value of 30.1 kilonewton meter, which is greater than this one here. Greater than that. I have a VR value of 53.8, which is greater than the 33.12. Great. And then I have my ESI provided, which is 3530, greater than this. So that means I'm going to have a deflection way less than L over 360, which is even great, okay? So there are my 3 values. They exceed what I need in order to make sure my beam is strong enough and it's stiff enough, and therefore, so this is how you write the answer. This is what you should be writing. In other words, you always put, again, the species, the grade, the size of the lumber. The only difference here is that because you are using a 5-ply, you have to tell me you're using a 5-ply. And then once you tell me what are the values, from the table, then you give me the MR value to see that it's greater than the MF value. The VR value is greater than the VF value. And of course, the ESI provided is greater than the ESI required. So, and that's done as far as the size of the beam. What's there left to do?
QF?
Sorry?
QR?
Design requirement.
In other words, what's left to do now? Are we done with our design? Bearing. Exactly. We always have to worry about bearing. Remember, like I showed you last week, there are 5 things you have to worry about: MR, VR, QR. And so you always have to worry about bearing, even for a beam. So therefore, we're going to move on to bearing. You'll see it's very, very similar to the joist. And I'll tell you guys what I do, and maybe you'll do the same thing. I'll leave it up to you, okay? So now, bearing length, the same thing that we did for joist. We know that design objective, QR greater than QF. Now, if people ask me, I'll repeat it again so you guys can have an appreciation. Here's, This is a very big beam here, okay? It's sitting somewhere here, okay? Hopefully either on a column or on a wall. And QR is a force perpendicular to the grain, okay? So that's QR. And therefore, if I look at this thing, what's the force I have perpendicular to the grain right now? It's my VF force, okay? And that's what you have to always keep in mind. Always say, what's the forces that is perpendicular to grain? In this case here, there's only the VF force, therefore it's only VF. So here we go. QF is equal to VF, 33.12 kilonewtons. And then I know that I said KD is 1, KS is 1, KT is 1, and therefore no modification factor. I can go straight to the bearing, okay? And I know that the QR, the big QR, which is the small QR times the bearing length, has to be greater than my QF value. So now here. Now guys, I like to always stay, personally, I like to just remember this number in the back of my head. So whenever I'm doing anything with bearing, I know that every time I'm talking about SPF, okay, every time I'm taking, I know that SPF is equal to 1.616, you know, the small QR value is equal to 1.616 kilonewtons per millimeter. So that to me is easy to remember. And since I'm always using SPF, and doesn't matter what species or what grade, I'm sorry, not the species, but what grade, it's always going to be the same value. Now, how many plies do I have? 38, and I have a 5 ply. So can somebody do the math? What's 5 times 38? I think it's about 190 about, right?
190 exactly.
Okay, 190. Okay, here they give you values for 191. So take this value here and multiply it by 5. What do you get?
0.805.
Exactly. So in other words, now what I like to do, okay, instead of worrying about, what I simply take this here, and I'll show you what I do, okay? And you guys can do the same thing, but if you would have taken this value here, they would have been both correct, okay? Because that's the width of the beam. So what I like to do is I say the QR value is 0.161 kilonewton per ply. In other words, for each 38 millimeter per ply, that's the value I get. So when I want to calculate LB, right, I simply take this. I'm sorry, I can't see anything down here. So I have 33.12. This is 0.161 kilonewtons per ply. And how many plies do I have in this built-up beam? I have 5. So it automatically gives me this number here. So I just remember the number of plies, and therefore I get my LB equal to, I can't even see because I've got all these things in my way here. Can somebody tell me that number? Because I got the little screen in my way.
41.1.
Pardon? 41.1? Okay. And guys, like, don't go over 1 decimal place, please. I mean, we're talking 0.1 millimeters. Okay, who's even going to see that? Here's my hair. Okay, so that means that as long as the beam sits at least 41 millimeters on its support, there shouldn't be a problem with bearing. And of course, normally we always provide more than 41 millimeters, but that's what I'm going to keep in mind for this beam. Does anybody have any questions?
No.
No, it's all good. Easy enough.
Sir, I have a question. This table, where did you get this table?
Which one? The small QR?
No, this table right here that you're showing on your screen.
Yeah, the like for the small QR value. I showed you that last week when we were doing bearing.
All right, thank you.
Okay, so in other words, when we were doing bearing last week, I pulled out this table. This is the value where you get the small QR value depending on the species and depending on the width of the beam, okay? This is where you get the small QR value. So when we talked about bearing last week, this is where it comes from, okay? I mean, if you're asking me where I actually got this table, I got this out of the handbook, okay? I got this out of the handbook, and of course, that's where I got the table from. But where does this table come from? Where did we see this table before? Last week when we were talking about bearing, we saw this table already once, okay? As a matter of fact, if you guys, I don't know if any of you guys are going to be interested in buying that handbook. If you go to the Canadian Wood Council, Canadian Wood Council what's it? Canadian Wood Council. Oh, I'll get you the website. But if you go there and you tell them you're a student, you're gonna get a student price for the handbook. Okay. And see, I'm lucky because not only do they give me a free copy of the handbook, but they also give me a copy of that handbook in a PDF format. You understand? So I can show you the handbook, and and out of the 3 handbooks that are like, I used to tell the students to buy, like the steel, the concrete, and the wood, I found that the wood was the one that was the best structured for, let's say, as a handbook. I find that there was a certain order on how the handbook was put together. The tables are very nicely put together. The examples are very well put together. The checklists are great, you understand? So it's, I find that out of the 3 handbooks, if I only had the money to buy one, and I know that I was going to be doing a bit of wood design, and if that's the only one I would be able to afford, I'd buy the wood handbook over the steel and the concrete, you understand? Because the other 2, they're all over the place. You really have to, you know, make, especially the steel, it's all over the place. And there's not very many good examples in there. And anyways, so I think that's it for example number 1. Hold on a second. I think that's it for today. I'm not sure. Yeah, so guys, at around 5 o'clock, I'll be sending you assignment number 2. Okay. Guys, I strongly, like I said, do the assignments. It's for your own good. It starts getting you ready for the test. It also gives you an idea of where you might not, you know, and it's, you know, I'm not forcing you to do the assignments, but you know, like it's, I strongly recommend that the best way to prepare for the test is the assignments. And of course, the test is only 2 weeks away. So, you know, keep that in mind. So, okay. And I think that's it. So let me put this,
Sir, for the good project, what are we doing? Like we just...
Well, I'm going to do that now. Like I'm going to open up another PowerPoint. Okay. And we're going to do the lab now. Okay. Rena?
Oh, okay.
So so don't worry. I'm not going to leave you. I just want to stop sharing. And so now, so, okay. Okay. So here we go. Share. Okay. Hold on a second. Yeah, I just want to be able to. Okay, so far so good. I mean, I hope. Oh yeah, guys, can I ask? Okay, did you guys all design your floor joists for this week?
Yes. I did.
Yes, sir.
Okay.
Yeah.
And what size did you end up getting?
38 by 235.
I think that's a good choice. I think you're on the right tracks. I agree with you totally. Okay, that's a good choice. So far so good. Okay. Okay, so that's, I just wanted to, you know, and guys, those of you that are not keeping up, I'm just telling you, you are going to really get inundated. Like I would strongly recommend that you keep up the work week by week. So this way you'll at least have the wood project and the steel project. Yes?
Is 38 by 140 all right?
38 by 140 is too small.
Fuck, okay.
Okay, that's way too small. So that won't work, no. 38 by 235, that seems to be in the right order of magnitude, okay? So.
Sir, quick question. 38 by 235 is what? Is it like a 2 by 8?
2 by 10.
It's a 2 by 10? Okay, that's what I got too.
Okay, so 2 by 10. In other words, like the reason why I say 38 by 235 is because that's what you see in the table. If I would say the 2 by 10, like I know what they are, like metric as well as imperial, but the last one you see in your table, that's a 2 by 12. The second to last one is a 2 by 10, and it's a 2 by 8, and it's a 2 by 6, and so on and so on. Okay.
Yeah, thank you.
Okay. Okay, so now that we've got our floor joist, and we know we're going to be using 2x10s, okay, or 38 by 235, and of course, as a matter of fact, I did it myself to make sure. Yeah, I did it myself, and that's what I end up getting also. So that's good. Now, so basically, so far, this is where we're at, right? In other words, we've decided to have a beam going down the middle, right? And then we decided that we're going to span our joist in this direction, and therefore our joist had, excuse me, had a span of 4.23 meters in both in the same way. Now, what you have to decide now, you know that we're going to be putting a built-up beam here because, guys, in residential construction, cheap residential construction, okay, built-up beams are what most people use because this way, when you order your joists, you order up the joists for the built-up beams, and it all gets delivered from the same lumberyard instead of you ordering a special, glue lam or parallel lam and whatever. So usually the built-up beams is the way that you go. Okay, unless you need to have like super big spans, you might decide to use a steel beam. I mean, but this is okay. Now, when it comes to built-up beams, one thing that you have to keep in mind is that they can carry a lot of load. So therefore, as far as a span goes, you have to limit yourself to around 12 feet, you understand? Even when you start getting up to about 14 feet, it starts being a little excessive for a built-up beam, especially if you want to stay within a 4 to 5 ply configuration. So what I tend to do with a built-up beam is keep a 12 foot span as being probably the maximum span for my beam. Therefore, I know that based on the like even if I'm carrying like 16-foot joists on each side of the beam, I might be able to get away with a 5 ply, understand? And always stay within SPF number 1, number 2. So basically, what I do in the back of my mind is this, okay? Is I say to myself, I want to stay approximately 12 feet spans, right? I have 42 feet, right? And therefore, this is about 3.5 spans. So I would, instead of just having 3 spans of 14 feet, which is, I would maybe look at maybe creating 4 spans. In other words, I would have a span there, a span there. So this is 4 spans, 1, 2, 3, 4. And that means that I would be putting columns. I would put 3 columns. And of course, and then they would be equally spaced. Like when I'm designing my columns, they would all be the same size. And that's how I break down the geometry for my beam. So as far as I'm concerned, so like I said, so I like to keep 12 feet as, same thing like for my solid wood joist. I don't like to go over 16 feet. I always limit myself to 16 feet for that. And when it comes to built-up beams, I like to keep 12 feet as, the limit of my span for my built-up beam. If I have to go more than 12 feet, well, then I'll see what the consequences are, how many plies I would need to get that bigger span. And if ultimately if I see that I can't get away with a 6 ply maximum, I wouldn't go over 6 plies. At that point, I would, and they still want to make it out of wood. Well, there are other types of, there's parallels, and there's all kinds of other, beams that are engineered that you can use. And if ultimately that doesn't work, I would probably use a steel beam, okay? So, and that's very common when you go into a residential house, you'll see that most of the beams are made out of steel, sitting on steel columns, and that then the floor is made out of wood. So don't be surprised if you have a hybrid of both. And the reason why I don't like to mix and match is because wood tends to shrink, steel doesn't, and then depending on how it's built, the shrinkage of the wood can start, being restricted by the steel. Then you can start getting cracks and so on. So right now, I'm going to look at this 42-foot one and say, well, I'll put a column there, I'll put a column there, put a column there. If the architect doesn't mind having 3 columns, or if the architect doesn't mind having 3 columns in his basement because he's not planning to finish the basement anyways. And therefore, by having the spans up to 12 feet, I will end up with a reasonable sized beam here, okay? So that's how I work out the, okay? So that means that right now, as far as my geometry goes, because that's the first thing I need to work out. Without any geometry, I can't do anything. So there's my geometry. I'll have a 3.2 meter span here, a 3.2 meter span there, a 3.2 meter span there, and so on. And then as far as the tributary width goes, well, it's very simple. Half a here, half a here. Here's my tributary width right there, okay? So there's my tributary width that the beam is carrying. There's the span that each beam is carrying, okay? And even though it might look like it's continuous, it's as if this is one beam, that's another beam, that's another beam, and so on. And of course, from what we said so far, was we had a dead load of 1.0 kPa. Is that correct, guys? Or am I?
Yes.
That's good, right? That's what we said so far, that our project,
Yes.
we decided that we're going to design the floor for 1 kPa. Of course, this does not include the weight of the beam, okay? And if at the end you're a little concerned about adding the weight of the beam to this, well, we can always go back and double check to make sure that the beam, you know, and I can show you how to do that. But you've noticed so far, guys, like you go to the table, you look for an MR value of so much, and usually the MR value is slightly higher than what you need, and you look at the VR value slightly higher that you need, and so that those slightly higher values can sometimes compensate for the weight of the beam. But if your MR value happens to be following exactly what your MF value is without the weight of the beam, well, I would see how much of an impact that might have on my final design decision, okay? So that's right for now, but in theory, I should make an allowance for the beam and add it to my dead load, but I haven't done that. I can add it here, assume something. In other words, I can assume, for example, I can assume 5-ply 2x12, which would be the widest, biggest one I would have. How much would that weigh per meter, and then just add it to my WD of my beam, you understand? So now we said that the live load is 1.9 kPa. Okay, so that's a standard because that comes right, that's the minimum live load that the National Building Code requires us to design the residential floors for. So we have 40 pounds per square foot. And of course, this is 20 pounds per square foot, a little bit more. And of course here, because they're gonna eventually finish the basement and, or they might put some kind of finish, there might be some ceramic somewhere on the floor that can be susceptible to cracking, whatever. I will limit my deflection to L over 360. And that's it. So now you've got your geometry, you've got your loads, you know what to do, and go ahead and size up your beam, okay? I'll tell you right now, guys, from what from practice, okay? You'll probably be able to have two choices, and both are going to be okay. Okay, I'm just letting you know right now. So one is you have two correct choices, but next week when I ask you what the size of the beam, and I'll tell you which one I would prefer to use, but then we'll talk about that next week. Okay. So does anybody have any questions regarding the lab?
Sir?
Yes.
You know how we do the geometry for every step you put on the PowerPoint?
Yeah.
Do we have to draw it for every step, or if we drew it once, it's enough?
Well, if you draw it once and then you show it to me all on one sketch, that's enough, you understand? But as long as, in other words, like as long as you keep adding to that geometry, you understand?
Yeah.
Okay, like, so Adriano, like what I'm saying is that you do it the first time, and then you do you drew a beam down the middle, and you show the tributary width for your joist, right? And then now you're going to take these columns, you're going to place them into your geometry, you're going to show me the spacing of your columns. Yeah. In other words, I need to see the geometry only once. It's up to you.
Okay. Perfect.
But what I'm trying to stress here is that this is something that has to be worked out before you can do anything else. Did you follow?
Yeah.
And I definitely, like, in other words, if you have a nice sketch at the beginning of your calculation, you have all the geometry shown nicely, yeah, that's fine. You understand? But you see how this thing kind of develops as you move along?
Yeah, every step there's something new.
Well, every step there's a little bit more thinking of how am I going to get the value to that variable that I need to be able to work with, right?
Yeah.
I mean, the textbook are great. They give you the span, they give you the loads and all that. And then the guy throws you the drawing and he says, do it. And he says, do what? I don't have the loads. I don't have the spans. Well, that's up to you to decide. You understand? And that's why I like to do these projects. It kind of sort of helps you visualize how this thing is put together just from the examples that you do in the class.
Yeah, makes sense.
Makes sense, huh? So does anybody have any questions? Because I'm going to put the video on pause now. I'm going to stop sharing. Put the video on. Yeah.